The idea of building a power scheme on Tasmania's wild west coast rivers has been around for 100 years. But it was not until the 1980s that the Hydroelectric Commission of Tasmania completed the Pieman River power development, one of the largest civil engineering projects ever undertaken in Australia. The 2,700 square kilometre catchment area extends east to the Cradle Mountain Lake St Clair National Park. It has an annual rainfall of 2.5 metres. The project would begin with 2 dams on the Pieman's major tributaries, the Macintosh and the Murchison, and a construction village here at Tulla. An intermediate dam would be built above the mining town of Rosebery on the upper reaches of the Pieman River. Due west, in the dense bush that once belonged to the Hugh and Pine timber getters, work would begin on the key piece in the project, a dam to store the massive waters of the lower Pieman. When the hydro came to town, no more than a few dozen families lived in and around Tulla. The hydro built 260 houses and a single men's camp for 900 men. The scheme would employ a workforce of 1,300 employees and 200 contractors. Many of them brought their families with them. A total of 2,500 people would live in Tulla at the peak of construction. The first challenge was the dam and power station on the Macintosh River. First, because the site was easy to get to. Well, relatively easy. But the geology of the U-shaped valley spelled problems for the investigating engineers. At the end of the Ice Age, melting glaciers deposited millions of tons of silty gravels in the valley to a depth of 30 metres. How far down was the rock on which the dam wall would be founded? What condition was it in? In the event, there was sound rock beneath the silt. The old weathered rock had been ground away by the movement of the giant plate of ice, leaving behind only rock that was hard and fresh. The dam would reach a height of 75 metres and back up the waters of the Macintosh River a distance of 20 kilometres. 10 kilometres south is the site of the dam on the Murchison River. There were no glacial deposits to create problems here. The rock abutments of the V-shaped valley would take a dam wall 95 metres high. This major trig station was the key point from which all the structures of the dam would be located. The Hydroelectric Commission had spent many years perfecting the technique of constructing rock-filled dams with water-resistant concrete faces. They were now regarded as world leaders in this field. All the dams on the Pieman scheme would be built using this technique. The concrete facing must be connected firmly to the rock foundation by means of a narrow concrete plinth, and the rock foundation must be made more watertight by drilling holes 40 metres deep through the plinth and injecting grouting under pressure to fill all the cracks and crevices. A laser beam was used to ensure that the upstream face of the dam wall was correctly aligned. Lake Murchison would have no power station of its own. Instead, its waters would be diverted into Lake Macintosh. This meant blasting and drilling a 1.6 kilometre tunnel through a rocky ridge to connect the two lakes. But the design engineers knew it was cheaper than building another power station. The 6-metre diameter horseshoe tunnel is designed to carry a minimum flow of 160 cubic metres of water per second. The concrete facing is built by the continuous pouring of concrete in front of a movable moulding known as a slip form. The concrete is delivered to the slip form by a crane and skip or by a chute from the crest of the dam. Men standing on the platform at the front of the slip form use pneumatically activated vibrators to rid the cement of pockets of air before the form travels over it, creating the smooth face of the dam. This technique of bathing the concrete with a continuous stream of water increases the hardness of the concrete by slowing down the curing process, and it prevents cracking by cooling its surface, which is exposed to the sun. Lake Murchison filled in a matter of weeks, its overflow pouring into what would become Lake Rosebery, the third and penultimate dam in the vast scheme. The dam wall would be only 75 metres high, but it had to span the Pieman River and the low-lying area on the right bank. During construction, the old Emu Bay Railway was used to move men and materials from one side to the other. Later, the line would be submerged by the waters of Lake Rosebery, so two new bridges had to be built, one across the Pieman River and another across the marsh below Bastion Dam. The bridges consumed 475 tonnes of structural steel and cost $4.5 million. Another Emu Bay Railway bridge on the Ring River, north of Renison Bell Tin Mine, had to be relocated so it wouldn't be submerged below the waters of the last lake on the scheme. So the hydro became involved in looking after some of the handiwork of man. The hydro also became involved in looking after some of nature's handiwork too. In the early 1970s, the Commission hired its first conservation officers. It was their job to work out ways in which damage to the natural environment, created in the course of carrying out large engineering works on roads and dams, could be minimised and, where necessary, repaired. The men had to be shown how to lift back and stockpile the often thin and fragile layer of topsoil from excavation sites. Later, this soil would be available to provide a seedbed for the verges of roads and other exposed areas. The revegetation program achieved great success, but not without considerable research and some trial and error. Each location had its own soil type, topography and microclimate. The main task was persuading construction workers to have a different attitude to the natural environment. They were accustomed to regarding nature as an enemy that had to be tamed. Nowhere was nature to prove more difficult than on the lower Pieman, at the site of Rees Dam. There was no road into the Pieman. As recently as the 1930s, the piners had journeyed in by boat, living in the bush for months at a time and floating the product of their labour downstream to Corinna. It took more than 4 years and 1.5 million cubic metres of earthworks to build a 56-kilometre road in from the Murchison Highway near Tulla on the northern side of the Pieman River. A temporary single men's camp was built on the southern side of the river, and a crew of several dozen men began preparing the dam site. The difficulty of getting into the site paled by comparison with the difficulties the men faced once they got there. The early investigative work had only hinted at the problems the geology of the lower Pieman would create. The Ice Age glaciers didn't reach Rees Dam site. They melted as they neared the warm waters of the ocean. So the weathered rock on the left abutment of the dam remained unscarred and unreliable. In places, the weathered rock was 40 metres deep. Removing it would have been a massive task and completely uneconomical. How to secure the dam to the left abutment? The design engineers decided to accept the weathered rock as the foundation for the dam. To make sure the soft rock was not eroded by seepage, The plinth was extended under the rockfill by means of a wide, reinforced blanket of sprayed concrete. As an extra precaution, the whole of the left abutment foundation was covered with a double layer of sand and gravel. There were other problems too. A landslip a short distance upstream made it necessary to relocate the tunnel that would divert the waters of the Pieman away from the dam site during construction. There were also problems with the Cofferdams. The floor of the riverbed had been deeply eroded before the Ice Age to a depth of many metres. Later, when the ice melted and the ocean rose, the drowned river valley was filled with gravel. Seepage was prevented by driving the sheet piles of the Cofferdam down to bedrock, 15 to 20 metres below sea level. Rees would be the biggest dam in the scheme, 122 metres high and 374 metres long. 3 million cubic metres of rock would be needed to create it. Finding suitable rock was not easy. A dolerite quarry site was eventually located some 5 kilometres upstream. The spillway of the dam was a major engineering challenge. 200 metres downstream of the dam, the river had been designated a scenic reserve. This meant that the sometimes massive overflow could not be emptied directly into the Pieman. Some other site had to be found. The only real alternative was Stringer Creek, which joins the Pieman just below the right abutment of the dam. However, the flow of water from the spillway could be 100 times that normally experienced by the narrow waterway. So something had to be done to protect it. The 112-metre chute would have built-in slots to aerate or soften the water, training walls to control the direction of its flow, and a flip bucket or ski jump at the bottom to toss it in the air and spread its impact. Of course, these massive civil works all had a single purpose: to generate power for the statewide grid. The power from Rees Power Station, like the others in the scheme, would be connected to the grid via Farrell substation. In spite of the problems posed by the geography and the geology of Tasmania's west coast, many of the elements used in the design and construction of the scheme were standardised for the sake of convenience and cost. The power station intakes, complicated reinforced concrete structures designed to get the water from the reservoir into the power station with a minimum turbulence and friction, were built on-site to a standard shape and size. The spiral casings are shaped so they deliver the water to the turbines at the base of the station with maximum impact. The turbines used at Macintosh and Bastion stations are virtually identical. The two 119 megawatt turbines used at Rees Power Station are larger, but their design is similar. So too is the complex technology that converts the motive power of the water to electrical power, then feeds it out of the power station. The Pieman development was nearing completion. Now it was time to fill the last and the largest of the reservoirs. It was quite an event. People who'd worked on the scheme, some of them for more than a decade, came to see it done. There were those who'd lived and worked in the mud alongside flooded rivers. There were others who'd made their contributions sitting over drawing boards in head office. Rees Dam would begin filling as soon as the steel stop logs were lowered into place and blocked the diversion tunnel. The $1 million steel logs had been built at the Moona workshops 20 years ago when the Mersey 4th scheme was under construction. This would be their 8th dunking. Later, a concrete plug would block the tunnel and the $1 million logs would be recovered for use on another dam. The school children and the grown-ups would be disappointed. It was not until the early hours of the next morning that the logs could be lowered into place. But there would be no delay in filling Lake Pieman. Flooding rains ensured that the dam filled in record time. The Pieman River power development had taken 12 years to build. 12 years in which an estimated 9,000 technical drawings had been prepared. An initial workforce of 68 employees and 13 contractors had reached a peak of 1,300 employees and 200 contractors by 1980. 4 reservoirs capable of covering an area of 60 square kilometres and of holding 18 billion cubic metres of water had been created. 3 power stations with an installed capacity of 391 megawatts had been built. The hydro began measuring the flow of the Pieman River at the Emu Bay Railway Bridge in 1927. 60 years later, that flow of water would enlarge the capacity of Tasmania's statewide power grid by 21% to meet the increased load of the 1980s and beyond.